Okay, so one of the one of the problems with the Laplace transform. Okay, so that we in the continuous time systems we use Laplace transform as we know. So one of the main problems of Laplace transform is not well suited for these difference equations. I mean, for example, in this equation we have this term e of k minus 1. So this is a delay term. Laplace is not the best fit for these kind of equations. It's good for differential equations that have differentiation and integration, but not very well suited for these kind of equations. So it's clear that we need another transform. So let's go through this some equations. Okay, so we know that the Laplace transform, which is in a sense a function of our two variables sigma and omega. Okay, we know that it's actually the integral of x of t, right? E to the minus st, which is e to the minus sigma t multiplied by e to the minus j omega t dt. So this is the equation of the Laplace transform that we all know from before. Okay, so let's do a little bit of math here. So we know that we are now transforming from the continuous time to the discrete time. So let's keep these sigma and omega as they are, and let's introduce, instead of this integration, we will introduce the summation from 0 to infinity, x of k, which is a discrete version of x of t, multiplied by e to the minus sigma k. Okay, we replace the time with the k, multiplied by e to the minus j omega k. Okay, so in this equation, I mean, what we have done is that we have just tried to discretize the equation. Okay, we have tried to discretize the equation of the Laplace transform and use the discrete index k instead of the continuous time index t. Okay, so this is the first step towards deriving another transform. Okay, so instead of having this term, which is e to the minus sigma k, okay, what if we can represent it this way, by r to the minus k? Okay, so what is happening here? So what we're doing here is that instead of using the variable sigma, I mean this intermediate transform is not an actual transform. I mean, it's just an intermediate step to reach the second transform that we are interested about. But for now, let's just keep with this. And in the continuous Laplace transform, this variable sigma used to indicate how fast the exponential decays or increases. Okay, here instead of sigma, we have the variable r. So r here, the magnitude of r will indicate whether the exponential will increase or decrease. So so we will rewrite this equation. So it will be summation, and then you have x of k, r to the minus k, e to the minus j omega k. Okay, so this is a kind of an intermediate step, and then the final step will be, okay, so we now know that these two terms, we can just combine them. So this is we can say this is r times e to the j omega all to the power of minus k, and we will call this variable z. So instead of having x of s, we will say x of z will be equal to the summation from k equals 0 to infinity, x of k z to the minus k. And this is the famous z transform, or the z transform, okay, that we are using, where z is actually r e to the j omega. So in earlier we had the s Laplace transform was sigma plus j omega, while here it's a polar form, it's r times e to the j omega. So what have we gained from this transform? Why is this transform actually useful? I mean, what is the benefit of using this z transform compared to the Laplace transform? Well, there is a very important benefit, because if we look at the properties of the Z transform, if we have a signal, for example, x of n, discrete signal x of n, and it has a Z transform x of z. So if we take the Z transform of x of n minus 1, it's equal to Z inverse multiplied by x of z. If we take x of n minus 2, it's gonna be z to the minus 2, x of z, and so on. So it's clear here that the Z transform can deal in a quite nice way with these delayed terms, and these were the terms that were appearing in the difference equations. Okay, so this very interesting transformation, okay, where we introduce this new variable z instead of s, has led to the fact that we are now we can deal much better with difference equations than the Laplace transform. Okay, so we can deal in a much better way than the Laplace transform. So if we go back to our proportional derivative controller, okay, if you remember in the discrete time, so we had, it was something like this. So we had u of k, it's equal to kp times e of k, right, plus kd e of k minus e of k minus 1 divided by the time, the sampling time t. So if we take the Z transform of this equation, it's going to be equal to kp times e of z plus, you can take kd over t as a common factor, and you will have here e of z minus z inverse multiplied by e of z. So it's clear that now we can arrange our terms, because in the controller, I mean in our controller, from an LTI point of view, the input is e of z and the output is the control signal u of z. So if we want to obtain now u of z over e of z, you can do it by very simple algebra, right? So you can just say that, okay, u of z is equal to e of z multiplied by kp plus kd over t, right, minus z inverse multiplied by kd over t. Okay, and in order to obtain u, the transfer function, which is u over e, is just gonna be equal to this term. So this is the transfer function. So now we have managed to obtain a transfer function of the controller, which we will call gc of z. Okay, this transfer function, which is gc of z. So why are we interested in obtaining transfer functions? Yeah, so it's the same reason that we were interested in obtaining transfer functions also in the continuous domain, because once we have a transfer function, okay, once we have a transfer function for each block in the system, so we have a controller, we have our system, we have our feedback system, and we can even have any other components inside here or here, and all we do is just we multiply those terms. So if this is gc and this is g and this is h, so we can use the block diagram transformations, simple algebraic rules in order to obtain the overall transfer function, for example. So it becomes quite useful to introduce the notion of transfer function in discrete time as well. But as we said, the main difference is that instead of using the Laplace transform, we use the Z transform, because it is quite well suited to the discrete time difference equations.